As Cassie mentioned, my name is Matthew Zimmerman. I'm one of the founders here at Farsounder and now VP of Engineering, so I'm responsible for all things related to our technology. Today I'm going to be introducing you to our 3D sonar technology, explaining how our technology operates and how it can be used to make navigation safer. I'm going to highlight a little bit of our product offerings and discuss some of the exciting developments we are working on. So, why 3D sonar? Well, groundings and collisions cost lives and money. And from those groundings and collisions, there are often major environmental impacts. What we're trying to do is provide the most basic information, what is underwater ahead of the vessel. Lots of advances in radar, GPS, and electronic charts have occurred over the past few years. These are great, but they still don't solve the entire navigation puzzle. We believe that 3D forward-looking sonar fills in the missing pieces of this navigation puzzle. So let's start by talking a little bit about the technology. Every vessel has a standard echo sounder. It looks straight down and tells you what the vessel just passed over, but it does nothing to tell you about the rock that's ahead under the water. Every large vessel, as you know, has radar. This is a great technology for looking forward above the water and around the vessel to see what types of obstacles might be seen above the water. However, it still does not detect that rock on the sea floor underwater ahead of the vessel. Some vessels have scanning sonars, also just called sonar by some commercial suppliers. Scanning sonars are a sonar, and they can be face forward. So technically, they could be called a forward-looking sonar. But they've really been designed for deep water fishing, and they don't provide a reliable navigation picture. So as you can see in this case, this type of sonar also can't detect the rock on the seafloor. To be an effective navigation tool, we have to have a system that can see from the seafloor all the way up to the sea surface. An effective forward-looking sonar must have a wide field of view, a fast update rate, and be capable of seeing that entire volume of interest with a single ping. So as you can see in this illustration, this type of sonar can see the rock on the seafloor. And this is exactly what Farsounder's unique technology can do. So let's take a closer look at what our sonars are capable of. Here's an example of our product's 3D sonar display. We generate a complete image ahead of the vessel to navigationally significant ranges. The idea of this capability is simple. However, the development of this capability was a lot harder than we thought. As I mentioned, I'm a founder in this company, and I've been working on the technology since even before Farsounder was born. It turns out development of our core technology was harder than we expected. The development took longer than we expected, and of course, the development also cost more than we had expected. However, today, we have a true 3D sonar product, and we've been shipping commercial off-the-shelf products to our customers all around the world since 2005. Our customers use our products to avoid a wide variety of navigation hazards, such as coral heads, rocky pinnacles underneath the sea surface or sticking up above, large whales, shallow sea bottoms, lost shipping containers that are floating at or just below the sea surface, of course, icebergs when navigating in polar regions, and other unmarked obstacles such as submerged breakwaters. Our products are intended to provide the vessel operator with a clear picture of what is underwater ahead of the vessels. As I mentioned before, our sonars operate at navigationally significant ranges and can create a true 3D image with a single ping. These systems map the seafloor out to at least 8 times the depth of water below the transducer module, as well as detect in-water targets out to the full range of the sonar. So let's take a quick look at our software display found in all of our navigation products. In this video here, we see the seafloor as well as a number of bridge pilings ahead of the vessel detected by one of our sonars. The seafloor has its color mapped to depth, where blue is deep and yellow shallow. On the left-hand side of the screen, we see our chart overlay display. Everything inside the sonar's field of view, i.e. that pi wedge, is real-time information ahead of the vessel. The display also includes a bathymetric trail to the side and behind the vessel, and we call this our local history map. On the right-hand side of the display, we see that same real-time sonar imagery ahead of the vessel, and this we call our 3D sonar display. The user can rotate the 3D image via a mouse or trackball, and a 2D slice through that 3D image is shown at the bottom of the screen in our profile display. The user can even select any bearing they choose using the profile selector, and that's the white plane shown in the center of the 3D image. This software is the same for all of our models. The Farsounder suite of navigation products are installed on a wide variety of vessels and consist of the Argos 350, the Argos 500, and the Argos 1000 sonars. The primary differentiator between all of our models is range, hence our appropriately named product names. These 3D forward-looking sonars have a maximum operating range of 350 meters, 500 meters, that's more than a quarter nautical mile, and 1,000 meters, more than a half a nautical mile, respectively. The maximum operational speed and field of view also vary accordingly to each model, as you can see in this chart. Each of the Argos series sonars use a specific in-water sensor, which we call the transducer module. The primary difference between the various model transducer modules is the number of elements in their receiver array. A larger number of elements results in a higher resolution sonar capable of operating out to longer ranges. The Argos 350 transducer module has approximately 50 elements. The Argos 500 transducer module has about 100 elements in its array, and the Argos 1000 has approximately 200 elements. All of our Argos navigation sonars utilize the same sophisticated sonar processing and display software and the same piece of inboard equipment, which we call the power module. A Farsounder supplied cable is used to connect the transducer module to the power module and features an underwater wet mateable connector, allowing the transducer module to be installed or removed by a diver. I know this is possible and not just designed in theory because I've done it myself. So now that you've been introduced to what our technology and products can do, let's take a few moments to talk about how they do it. Other forward-looking sonars are based on 2D technologies, much like a radar image, but underwater. These types of sonars can only generate an image at the signal level versus range and angle. In this example here, we took real signals from a single ping from one of our sonars and processed it with traditional 2D beamformer processing, as shown on the left. And our 3D beamformer processing is shown on the right. This ping was transmitted when the vessel was approaching along a commercial pier. In the 2D image, we can see a strong reflection corresponding to the location of the pier, as I've marked with this dotted line. However, with only a 2D sonar, we can't determine how deep the object is, only where it's located. In the 3D image, we can see those same features in the horizontal slices, as well as the seafloor ahead of the vessel in the vertical slices. We can also see the raised structure of the pier wall, showing it extending from the seafloor all the way up to the surface. As you can see, the beamformer processing output is pretty complicated. It's a lot of data, and it takes some effort to interpret this data. So that's why we've developed a further processing stage, which we call target modeling. With this stage, we convert the 3D data into 3D information. On the right, we can now see the standard 3D output of our system from this exact ping. In this case, the target was a pier wall and clearly visible above the water. However, if this had been a real underwater obstacle, a traditional 2D processing would not be able to tell you if the object was deep and therefore safe, or shallow and therefore dangerous. So as you can see, our focus is primarily on being a real-time sensor ahead of the vessel. But I mentioned that our products also include our local history mapping feature. This feature is essentially a bathymetric survey of where the vessel has been recently, and it's similar to the output of a standard down-looking survey sonar. We store the most reliable detections to build this map. This can be used for retracing a difficult passage through a treacherous route, or performing an anchor survey before dropping the hook in an unfamiliar location. Local history mapping in our current products currently supports 1 hour of history. We have some software updates in the works that will enable the ability to store and recall more than this 1 hour. In the future, we also envision the ability to store, recall, and share data across a fleet. This could be exciting for commercial operators, allowing them to share the sonar data with other vessels in their fleet, and also for yachts. Yachtsmen could now share the information with other vessels under the same management company, or even with your own cruising club. Besides the local history mapping capabilities and our future plans we have for it, we're also collecting data in another way. This is our expedition-sourced ocean data collection program. This program is open to a select number of our customers who are already going to a lot of exotic locations. These customers are interested in contributing to science and want to participate in making our systems better. The participants of this program are given a USB hard drive, which records all the raw data coming off of their sensor. They then send it back to Farsounder for compilation. Here's a map of some of the data collected by our customers. We have many terabytes of this sonar data, and it's collected from all over the world. This data is used in our continual testing of our algorithms so that we can test these algorithms with different sonars from different locations, different conditions, and different environments. With our customers' permission, a subset of this data is submitted to the IHO and NOAA crowdsourced database through our work with the Crowdsourced Bathymetry Working Group. Farsounder is an official trusted node of the NOAA IHO program, and all of our contributions, along with the rest of the contributions to the database, are available for public use, and they also get passed on to the Seabed 2030 initiative. So how could this crowdsourced bathymetry be useful? Well, clearly, our sonars can detect major features and navigation hazards. Here's an example of some of the data we've collected locally here in the Narragansett Bay. This type of data is invaluable if the area was not well charted or not recently charted. This way, hydrographic offices can look for discrepancies and plan their official survey needs. However, today, we have other survey operators using our systems. We have an official integration with the Kinsey product from QPS. This integration offers a real-time connection to the QPS ecosystem. In there, surveyors can include Farsounder data as part of their overall survey process. As I mentioned, our products are installed on a wide range of vessels, operating all over the world, from the hot tropical waters all the way up to the cold polar waters. Many of Farsounder's customers also have ice-classed hulls, and most of these customers take advantage of our standard fixed mount installations. A few of our customers even have full ice-breaking capabilities. These customers usually install the Farsounder on a retractable hoist. In all cases, these customers rely on their Farsounder sonar to help them navigate safely. Different types of our customers include passenger vessels, research vessels, yachts, military and Coast Guard vessels, survey vessels, and other offshore service providers. As you can imagine, different customers have very widely varying different hull types, and we can easily install our equipment on a variety of these hull types. Here's a couple examples of vessels with a raked bow, showing the fairing installed on the centerline, with the tube of the fairing recessed into the top into the hull, with the top of the fairing tube mated flush to the system. Here are a couple more vessels with a raked bow. In these examples, the fairing tubes are mounted to the side of the stem. We provide drawing packages for all of our sonars with a variety of installation examples. We also have an installation design guide, which walks customers through the most important details. And most importantly, we also offer a complimentary review of all installation drawings. We're even happy to provide this service before an official order for far sounder equipment is made. So here's a few more vessels, another one with a raked bow. This time we see an example of a fairing that was installed on the center line, but forward of the stem. This vessel was a quick refit and the stem was not cut. There's only a small cable penetration going through the hull, and inside the hull, the cable runs in a conduit up above the water line to prevent any water ingress. Here's a few more examples of the fairing forward of the bow. In this case, there's a camera housing installed below the sonar fairing. Locating the camera housing below and behind the sonar prevents turbulence generated by the camera housing from interfering with the sonar. Here's another example with both those fairings recessed into the hull. Of course, some of our customers have very straight axe bows. These pictures show an Argos 1000 installed with a rectangular fairing tube on the vessel's center line. Here's another example of a straight bow with an Argos 500 installed on the center line. And of course, many of our customers also have bulbous bows. This picture, the large one on the left, shows an Argos 500 installed on a 62-foot composite hulled Nordhaben. The other two pictures show vessels with medium-sized hulls, which have far sounder equipment installed. Here are examples of vessels with large bulbs. The two hulls at the left and right are ice-classed passenger vessels. And it's even possible to install on a bulbous bow to the side of the stem. We found this picture of one of our customers on the marinetraffic.com website. And lastly, a few of our customers, as I mentioned, do choose to install our equipment on a hoist. This is useful for ice-breaking vessels and other special applications. At the left is an ice-class yacht with an Argos 500, and on the right, we can see the hoist from the RSS Sir David Attenborough with an Argos 1000. The Argos 350 is designed to fit inside a standard 10-inch diameter sea chest and can use off-the-shelf hoist equipment. Owners and operators are always concerned with minimizing risk, and I hope I've been able to show you all how Far Sounder's navigation sonars are key contributors to vessel safety, and they're easy to use and install. By helping to avoid collisions and groundings, we can minimize ship downtime, reduce injuries, decrease environmental impact, reduce the frequency and severity of these claims, and save a variety of indirect accident-related expenses. All of these mean contributing to an improved ROI. Regardless of whether you're a commercial operator or a yacht owner, keeping your vessel in operation longer and more safely makes economic sense. So thank you everybody for taking the time to learn about our technology and how the Argos products really can offer you a safer navigation experience. I'd be happy now to answer any questions that I can.
Thank you, Matt. That was great. Very informative. I hope you all enjoyed that. So we have a question here. When do you expect to have operational capability at more than 25 knots?
Well, that's a great question. It turns out that as vessels go faster and faster, they need longer and longer range capabilities because they need more time to make a decision when they're going that fast. Or rather, they need at least the same amount of time, but it takes a longer range to create that same decision time. We have been in discussion with some customers for some very high-speed applications, and that may come along in the future. If you have a specific need and a specific application, please feel free to contact us after the webinar, and we'd be happy to discuss possible options.
Great. I have some more coming in here. Can you confirm the 10-inch sea chest?
Yes, the Argos 350 is designed to fit in a standard off-the-shelf 10-inch diameter sea chest. It can be ordered with two different configurations for the transducer module. One configuration has the connector on the back, and that's suitable for our standard fixed mount installation. The other configuration has a connector on the top, and that's designed to fit with a hoist mount installation. There are a number of off-the-shelf hoist mechanisms that can be used with an adapter plate for our Argos 350. And our Danish partner actually has a Argos 350 specifically designed hoist that he has available from his company.
Great, thanks. And then we have another question. Can fishing nets be picked up by the sensor?
Unfortunately, in most cases, nets are not going to be detected by the sonar. Nets are really difficult sonar targets because they have almost no reflectivity.
Okay, great. Okay, a couple more questions here. Do we have online training for the bridge OOW using your equipment?
Great question, and a very timely question. We are working on finishing up an online training program. We expect to launch around the end of this month the first training program for dealer technicians. And then early next year, we'll be releasing a similar program for customers and crew. This will be an online program. It will be free and available for all participants, and it will walk them through all of the hardware, software, and interpreting the data. In the meantime, if we have customers that do want some end user training, we can also offer a remote end user training session. This typically consists of a remote team viewer session to the bridge computer and a video conference with the crew, and lasts between 45 minutes and an hour and a half, depending on crew availability and their questions.
Great, yeah. Okay, so what is the maximum depth that it can be successfully detect the bottom?
Our products currently operate down to 50 meters, 50 meters, so that's about 165 feet. My teammates hate it when I say this joke. I use it to death. But if your draft is more than 50 meters, then you're already a shipwreck. 50 meters is plenty deep for standard surface ship navigation. It's also beyond the recreational scuba diving depths. Some of our customers use the sonar to find unmarked or unknown scuba diving locations, such as pinnacles and atolls coming up out of much deeper water. And they can use the sonar to find these locations for their passengers and guests to dive on.
Okay, another question is it possible to simulate the operation of your sounder on a modern bridge simulator for training purposes?
The short answer is yes. Right now, we have a utility which allows these types of customers to play back previously recorded data and process and display it in real time for training purposes. If they want the data to be simulated specifically to tie in with a simulated route, that is a harder problem that we can provide, but is a little more expensive.
Okay, great. At what frequencies are the sonars working? Can the sonar interfere with porpoises echolocation?
Good
a large
question.
number of ships using the sonars, yeah.
Good question. Our equipment operates at about 61 kilohertz. This is a little higher the frequency than the most common sonars, which are 50 kilohertz echo sounders. Our equipment operates at a lower transmission level, a lower source level than these other accepted marine electronics. We're operating at a slightly higher frequency, which is more benign to the environment. We're pinging less frequency and with less energy. So specifically, can porpoise and dolphins hear our sonar? Yes, they can. We operate in a small section of their hearing range, but we are quieter than the dolphin or the porpoise's own sounds in those frequencies, so we could never hurt them. We actually began developing this technology with the environmental impact in mind. We're located in the northeast of the United States, where we have a severely endangered North Atlantic right whale population, and our original prototypes were designed to help avoid hitting these whales. They basically don't die until they're hit by ship strike. So we wanted to develop a technology that could avoid hitting whales. Also around the time that we started working on our technology, there was an oil spill locally from a barge that had hit a rock and caused some damage to the barge, spilling oil. In the world of oil spills, it was quite small, but locally it had a huge impact. So from the beginning, our mindset was, how can we help vessel operators be more benign to the environment around them? How can we avoid hitting whales and hitting rocks?
Right, right. That's great. Yeah, and within that vein, we have another question. What about large mammal life, e.g. whales, example?
So the great whales, we're out of their hearing range. They can't hear us at all. Sometimes sonar, you may hear some negative connotations about sonar in the media. Anything which uses a sound pressure wave to make a measurement is a sonar. And the frequencies vary tremendously from very low frequencies to very high frequencies, and the energy outputs vary tremendously. It is generally accepted by most scientists around the world that very loud, low frequency sonars can have a negative impact on marine life. That's not what this type of sonar is. We're a mid-frequency sonar, we're very quiet, and we put less energy out there than the other systems that are already accepted around the world.
Great. Okay, and then we have one, do you have a lot of false echoes?
We have real echoes from reflections in the water column, but those reflections may be from things that you're not interested in, like bubbles and waves. We work really hard to reduce these false detections of navigation obstacles, and our software does pretty sophisticated processing to avoid them. On our website, we have a whole slew of real videos from different environments operating all over the world. The vast majority of those videos are using our auto squelch settings, where the software automatically configures the best settings for themselves. However, there is also a manual setting that allows the operator to raise that detection threshold to increase the squelch. This is very similar to the radio that we have on board. If you turn your squelch down really far, then you pick up a lot of quiet signals and static and noise. If you raise your squelch up higher, you will remove those. You can also think of this very similar to wave clutter on your radar. By adjusting your clutter adjustment, which is also a squelch, you can reduce those false detections. Very similar with the far sounder sonar.
Okay. Okay, we have a question on integration. Can you integrate with an ECDIS rather than the display?
Yes, so the videos we showed in this presentation were outputs from our software's display. We do integrate with a number of other systems. As many of you know, integration is a very relative term. So we have direct integration with the NACOS Platinum by Wärtsilä, where inside their software, they have a far sounder 3D sonar display. They don't yet have chart overlay, including sonar, but we expect that to be coming in the future. We have the direct integration with the QPS Kinsey product, which is not an ECDIS, but is a real-time survey tool. We do have legacy integration with the Sperry Vision Master systems for our legacy products. And we do have a couple of other big name ECDIS systems, which we expect to be announcing in the general future. There are also mid-level integrations that we do with companies such as Team Italia with their iBridge, as well as Boning with their Boning systems, where they use virtual buttons and touch panel displays to interact with our software on their bridge systems.
Okay, great. So I have another question about Navy. It's I'll read it exactly what it said. You may be a submarine and not a shipwreck. Do you have any naval customers, divers, ASW, or mine warfare?
Great question. So our current products are designed for surface ship applications, but they could be directly applied to subsurface vehicles, whether manned or unmanned. We do have one customer that is using our equipment on a manned submersible, and one customer using our equipment on an unmanned submersible. we'd be happy to talk about your specific application. We do have a software developers kit with a machine interface to all of our 3D processed information. So the processed sonar data could go directly into your vehicle control system. True whether it's a subsurface vehicle or even an unmanned surface vessel. If you do have a specific project in mind, please contact us. We'd be happy to discuss in more detail with you.
Absolutely. Okay, what type of sea bottom is not picked up, if any?
That's another great question. Basically, you have to have a seafloor that is hard enough to make an echo. So if you've ever done any scuba diving in a muddy riverine environment, the type of place where you stick your hand into the riverbed or the seafloor, and you're not quite sure where the water ends and the seafloor starts, well, you're not really going to get any reflection back in that environment, and you won't get good bottom returns. But in pretty much all other environments, you will. We've done extensive testing around the world in freshwater, in saltwater, in estuarine environments. We've done testing in rivers in Europe, rivers in the US, and all over the world. So rest assured, we've really worked hard to make sure the equipment is effective in a variety of environments. If the seafloor is too soft to make an echo, then it's probably not going to be a significant navigation concern to you. But if there is a hard feature embedded there, we will detect that. I like to tell one anecdote from some testing we were doing on the Atchafalaya River in Louisiana. There was a railroad bridge crossing the river, and a few years before our testing, there was a barge coming down river with a crane on the barge. The crane was about 6 feet higher than the clearance under the bridge, and when the barge came under the bridge, the crane hit the bridge and was pushed off the barge into the shipping lane directly under the bridge. The Army Corps of Engineers sent down salvage divers pretty quickly, cut off all the tall structure, but they left the big counterweights down on the riverbed. And the Atchafalaya River is one of those environments where in the main channel, it is so soft and silty, there's almost no reflection. While we were there, we lined ourselves up with the bridge upriver. We found the dent in the side of the bridge and just headed on that bearing. And lo and behold, we had a huge reflection right where those counterweights were. So from a navigation point of view, if there is something hard in there, we're generally going to see a good reflection.
That's great. Okay. So what is the cost of the Farsounder 500?
The list price for the Argos 350 starts at about 55,000 US, and the Argos 1000 is about 176,000 US list price, and the Argos 500 is obviously in between. We have an extensive dealer network around the world that we sell all of our equipment through, so these dealers can give you an official quote. We provide the same pricing to all of our dealers, so you won't really find any dealer with any better deals from us. Of course, our different dealers do offer different levels of value-added services, project management, installation, commissioning, training, and so forth, and they can quote you for those services as well.
Great. And we have a question. What is the smallest yacht the system is capable of practically being installed on?
The Argos 350 is designed for about 14 meters and up, so about 50 feet and up. The smallest Argos 500 customer we have is a 62-foot Nordhaven. That's about a 20-meter vessel, so we can go quite small.
Great. Okay. Are the sonars also prone to errors in the case of echo sounders?
I'm not quite sure. I think the question probably is asking about interference. And the answer to that is most echo sounders, the most common frequency for echo sounders are 50 kilohertz. And after that, 200 kilohertz. Our systems operate at about 61 kilohertz. So we generally recommend that echo sounders are installed behind the far sounder so that they don't have interference from both the directional point of view and from the spectral, the frequency point of view. If you do have another vessel directly in front of your sonar, pinging with a 50 kilohertz sonar, it is possible that you might pick that up a little bit. But if they're directly in front of you, you're not really concerned about using the sonar for navigation in that case.
Good point. Okay, so what is the weight of the system?
I don't have the exact number off the top of my head, but the transducer module for the Argos 350, I think, is about 18 kilograms off the top of my head. And the Argos 1000, I think, is 36 kilograms, somewhere in that ballpark.
Great. All right, I think that's the last question.
Well,
Lots of
Kathy,
great questions. Yes,
thanks
lots
for
of-
the introduction and the moderating. Thank you, everybody, for taking the time to join us and learn about our products. If you have further questions, please don't hesitate to call or email. We'd be happy to answer whatever we can for you. Thank you, and have a great rest of your day.
Thank you, everyone.